variable to change x into
yeah.
Indeed, if you compute the post-selection probability for computing +1, it's the largest one, while post-select -1 is the smallest one.
Okay. Yeah, I see.
Actually, I wanted to make a comment for you. Before you were asking about the meaning of data which is infinity, right? And so to do this computation, we have taken the meaning of the thermodynamic meaning text. And you see that you get some results that beta becomes 1/2, or it becomes at the end another 1/3, which is not compatible with the product state. No, because for a product state, you can expect the correlation function to be
zero.
And this is an example of a case where taking the thermodynamic limit first and the beta limit after is
So basically, because going back to the question, you are right, you are at the critical point, h fixed equal to 1, that's why it's not symmetric.
Yes.
Of course, if you take it minus 1, you will get the opposite result.
Yes. Okay, so now, just to summarize, marginal perturbation, meaning logarithmic growth of the entanglement, just with a different factor, and the common law to algebraic correlation function, just with a different dimension. So it means that if I compute the correlation function, is not anymore 1 over 4, but it continues to change the function. Okay, so now let's see what happens in a different case where the perturbation is not marginal anymore.
Question. So this is all predicated on the assumption that we are measuring on every single side. And what if you have relaxed this condition, having measurement on subset of the sites?
Yes,
The result
will be the same. If the I will read the paper tomorrow, for instance, and if the effect description again is the excellent effect line, the result is as far as the effect line is an epsilon, exactly an epsilon, and the measurement outcome can be constrained to exactly 1, then it's
so basically, I guess you rescale essentially.
You rescale, yeah, exactly. Okay, so now we see the second case. Here we talk about the okay, so the second case is when we have when we measure the measurement operator contains z, not epsilon. And so the defect line, if we use again this dictionary here, selecting again nj plus 1 over j. and the defect line is yes, sigma. And now this has a dimension 1/8, this has a dimension -1, so the screen dimension is negative, and this corresponds to a relevant perturbation. Maybe it's relevant perturbations. Now, if you want to study relevant perturbations, and there are, in this specific case, there are two ways to do it. Or you study what happens at the small beta regime and use a Euclidean approach. Or you study what happens in the large beta regime and you can use some approximation of the wave function. Actually, this can be always done. If everything behaves nicely, these techniques, these approaches can always be used. So we start from the small beta regime, and then the large beta regime. First, we keep the same result. So small beta. Basically, what this perturbation does is the following. We start from a safety, and then we have an energy flow, and this energy flow basically ends up into a new fixed point that in the Euclidean language under the name of boundary conformal theory. Now, what is a boundary conformal theory? We are doing measurement along this tau zero line. No? And the measurement is relevant. So it really means that we are doing, we are pinning our spins along the boundary. And if the perturbation is relevant, this pinning of the spins at the boundary, what actually does is cutting your space-time into the upper plane and the lower plane, just because it's a relevant perturbation. So also the small values of beta. Practically, this measurement is like, yes, in the upper plane and the lower plane. So this is the regime in which a defect becomes a boundary. And so then if one knows what is the behavior of the easing conformal field theory in the presence of the boundary, you can ask, okay, how does the screen dimension change, for instance? So basically, in the small beta regime, we have the problem of measurement of artificiality to a problem of boundary conformal field theory, where we ask the decay or the behavior of correlation function along the boundary. Because not we want to fix the correlation function between this point and this point. So correlations along the boundary. And yeah, actually, for this specific boundary, for using everything is known, and what we predict using again this dictionary here between sigma and z, that correlations, the kinetic correlations, decay as J minus K to the power of -4. So they became much faster than before. Appeals xj, xk, and then correlated becomes J minus K to the power of -4.
And if you computed the y, it would also be -4, or
Yeah,
is there a reason why it's like isotropic?
I think the reason for which it's isotropic is because I mean we are bringing all of the strings along the z direction, and if you rewrite every power operators in terms of z, okay, for y, okay, zx, the product of zx, dy, dy, so okay, so this. Yeah, I think the fact that you are using this degree of freedom is not with some constraints on the directions. Like, because for instance, if you measure in the x basis, even though it's marginal, but also if you take a different theory and measure in the x basis, you get different answers depending on these correlators. So I think it's a property of this flow to this specific boundary.
Because this state doesn't have a symmetry on the spin that we are bringing the z to symmetry.
Yeah, yes. Yeah, and here also the one-point correlation function is not zero. Because we are taking this. And the effective central charge is also zero, the entanglement in the low. Here we can look at the properties of Gaussian states because we don't
So how do you compute this central charge? There is other methods of using it.
So one possibility is to understand again from a good theory point of view, like if you construct your replicas and then you have to compute the same dimension of the field that was from one replica to the other. And since there is this, so basically like, we have your replicas. And I'm cutting we can say that each of these boundaries basically the coupling of these two, right? And so this means that usually the replica space it works that you go from here if you are taking the plane, there is no way to go from one replica to the other. So the field is just identity, and if this field is identity, yeah, so I'm not giving a lot of details about the boundary conformation theory techniques because to take another course just on boundary conformation theory. let's try to see what happens in the large beta regime where it can be smaller than lattice level and getting the same result. Again, because this flow is like there is no a discontinuous point, like there is no intermediate fixed point. Okay. So in the regime of large beta, let's see what we have to do is take this Hamiltonian here and do an expansion in the limit of large beta. It's very similar to what I was saying before, that we take non-unitary operator and the limit to the regime of small u. Now we get the regime of large u. And so if we do it, what we get is so the cost management function is not So Z is just a product state when for instance we have up. Then U is the minus beta. So beta is going to infinity, U is 0, and we get just a Z state, which is what you would expect if you do projective measurement of this outcome. And BJK is called the strange correlator. Is the correlator between Z and C divided by Z. It's actually the connecting version of this. To subtract the So the way to derive this is the following. You break down psi C, for instance, in the decay system. And then you start to act directly with these specific operators, and then you try to sum of all these. And now let's see, for instance, how you can get the correlations from here, and then put it the I think let's here. Okay, so suppose it ranges in Xj, Xk up to one side. So the trick is very simple because if we expand this, so we get z e to the minus 2 squared over j k b j k x j x k. Then we have x j x k. Actually, is also commute, so this. Just because these objects commute from x, so I can here. If you expand this object, we can see that the connecting collector. This is non-zero only when this is equal to this and this is equal to this, such that they square to 1 and the correlator is 1. Is it clear? If you find this object, now we get the somewhere, let me give it differently, somewhere LL, DLL, XL, XM, XJ, XK, Z. I mean, these X operators here, they flip one spin. No? And so, in general, when we overlap with the other operator here, it's 0, because we have on one side of spins up, and the other side, on the get, we have flips and spins. So the only way to get a non-zero contribution is to annihilate basically the contribution coming from X. And so it means that only when, for instance, L is equal to J and then is equal to K, we get x squared, which is 1. And so then this doesn't act on the figure state, on the z state. So this is exactly djk. And djk, I haven't told you, but this dk says 1 over j minus k to the power of 4, which is exactly what you read from BCIT, from component physics. Okay, so the last thing that maybe I said today.
Sorry, this is the first non-trivial element. What about
They are
expansion of the EU? But
yeah, this is
because of your also the other all the terms.
yes, but it is yeah, this is an organic square. And also the fact that we know that this should be the result.
And here, if we did minus beta or beta going to minus infinity, it would give the same meaning because of losing the symmetry.
Yes. Yeah, so here was selecting plus 1 and minus 1 would be the same.
And could you both select for like a nil state, for example, or this then is not possible to do in the field theory in this boundary?
So one could do this, but the boundary information theory towards which you flow, I think could be very different. It shouldn't have these problems. I haven't looked at it numerically, but from the theory side, we expect it to show to a different effective. But there is something not hidden that when we observed this result, we were very puzzled. Like, and I told you that the effective central charge is 0, so we have an area of behavior of the entanglement. But I've also told you that the relation function decays power laws. And this is somehow counterintuitive because usually, like when you think in terms of area law and value entropy, you think about exponentially decaying relation function. So how can we reconcile the things? And to match these two things, it was useful for us computing the particle Hamiltonian of
the particle.
The particle Hamiltonian, yes. Because
You say particle Hamiltonian, you write the active state as a Gaussian state.
no, I write the Hamiltonian having this as ground state.
Okay. Which is the same. It's the same. Yeah. So the state is Gaussian, so the product Hamiltonian is the term that I choose. The BJ.
Well, this state is not Gaussian.
It's not Gaussian. So.
No, because this BJK is not Greenwich.
Okay.
Yeah, exactly, it's not Gaussian.
Of course.
It cannot be Gaussian because the field is not Gaussian. So the technique to write, the method to write this parent Hamiltonian is called the Bitten conjugation method. And it's so you start from a state Z, which is the unique ground state of this Hamiltonian, which is 0, which is gamma J, gamma J, where gamma J is 1 minus Bj. It is actually the desktop, so this is sum for J, gamma J. So Z is the ground state of this Hamiltonian here, H0. We then define any set of operators that we call gamma bar J, which are e to the So basically, you apply the same unit, like it's like you are constructing the state starting for this psi. You compute first the parent Hamiltonian of ZZ, and then you sandwich with this unitary operator. Also, this satisfies the properties that the square is equal to itself. And so then the Hamiltonian is simply given by sum over J, gamma bar J dagger, gamma bar J. So if you want to make abstraction, this parent Hamiltonian is that as a dark state. And so then the limit of the mass division operation, the limit of that theta of mu, this can be written as so minus sum over J is Ej plus V square sum over J different from K, Vjk, Xj, Xk. So again, for equal 0, we get the Zeeman term. Now whose ground state is given by, let's say, all the strings pointing up. As we turn on U, basically we turn on some non-local interaction, where you see that the power of decay is very, very fast. It's 1 over J minus K to the power of 4. And it's so like we have a system which is in the short range physics because this BJK decays very fast, and this is why we get an analog behavior of the entanglement. But at the same time, the evaluation function inherits the power of decay coming from the function. So in other words, if we want to put together the fact that we have power of decay of the evaluation function and RLO, we have to think that the current Hamiltonian is a combination of short range plus correction function decaying very fast. So basically, just to summarize, we have seen two cases very different one from each other. Like the case where here we have X, and this gives rise to a marginal perturbation, and when you have a marginal perturbation, usually it's the most tricky thing that can happen because we need some way to study for any kind of measurement strength, which is the behavior of correlation function or entanglement. And then we introduce another class of states where basically the operation, the measurement that we do corresponds to relevant perturbation. And usually when we have relevant perturbation, or we rely on CFT methods, and so if we just know the boundary of the theory, we can derive what happens. Or if you know that there are no intermediate fixed points, like we don't expect that something non-trivial happens for a finite vector beta, as is the case in most of the simple critical theory that we've studied so far, like liquid critical theory, then we can go to the large bit regime and take this expansion. And they should be different about that.
So again, I didn't get why you, or how do you apparently come to understand these conflicting ideas?
Because it has a part which is long range.
Sorry? Yes.
Because it has a part which is long range. Like this case, that one of the general escape the power of 4.
This over, okay, the parent.
The variant. And the base diagram for this model has been studied, the basic case. And this one, so basically, if this power law was, I think the bound is 1, like if it decays faster than 1, then we have a very good growth of the entanglement, even though we are not, even though we are in the X phase. While if
it's because it is itself, it is the interaction which is long range.
yes, exactly, yes.
Okay.
So this somehow includes some long range.
There's a tree, so there are degrees of freedom which are basically created by the laboratory itself, which
Yes.
are correlated. Okay. So in these degrees of freedom, this is the correlation are low for the second. Because, well,
Well,
but it's,
I need plus 4.
if you look at the degrees of freedom that is electron is
Yeah, the problem is that this is art, just like.
yeah, just very okay. So if you look at other correlation functions, you probably higher order of correlation function, you probably would see scaling behavior which is not. I would expect scaling behavior which is not algebraic, is it? Right.
So for instance, the variance is.
Yeah, exactly.
Well, what I can tell you is that we look at the variance of BJK.
No, we have already at the local correlation functions here. If you look at the for all the correlation functions,
But for instance, like XJ is exactly as BJK.
the fourth. Okay. No, that the higher order of the 2 point. The fourth point correlation function. I mean, to justify because the entanglement in a sense is right.
You mean we need all the.
Yeah, it's sort
all
of
the
the order of correlation function to know how maybe the entanglement is being.
I'm not very sure because anyway it's a boundary conversion of fields. But it's true that I don't know how what is the behavior of the correlation function. But I mean, it would be weird to find something that behaves exponentially if we're still in the regime of a CFT.
Yeah. Okay. Yeah, we expect anyway some exactly.
But it's still dependent when you look at the working question. I think in this regime, like, I think the logical regime one can extremely important now. In the regime of SFT, I think. And
Okay, so for today we are done.
yes, we are.
Sara is here for 3 days until Wednesday, so if you want to talk to her, she's in the Ammezzato office. And yeah, so thank you.